Hello class. Topic 10 is on Euler's approximation. Some first-order ODEs are not solvable using analytic techniques. So the strategies we've been learning, such as the integrating factor, separation of variables, if it's an exact equation, some of these things aren't effective in solving a differential equation. However, solutions can still be approximated by using a numerical method known as Euler's method, demonstrated below. Now what we're going to be working with here is a very simple differential equation that you see right here. This is the Malthusian model. It's y prime equals a constant times y. Initial condition is given, y of 0 is 2. Now we know the exact solution to it. It's a pretty easy equation to solve using separation of variables. And over here you're seeing a graph of the exact solution with a few points emphasized. We're going to practice a technique, Euler's method, to approximate the location of this point and then this point. And we're going to do that by effectively filling in the missing y coordinates of this table here. And I'll explain what this is for in a second. Now the way we're going to do this conceptually is we're going to find the tangent line right through 2. So the line that's tangent right here to our solution. And we're going to use that tangent line to predict the y coordinate. Now keep in mind, when you have a curve and you have a tangent line, right, the further you get away from where the line is tangent, you have great potential for a curve pulling away from that tangent line. But if you stay relatively close to the tangent line, then you can use the tangent line as a way to approximate the curve. And we're going to do that exactly in this case here. Use a tangent line to predict where the next point's going to be. And then what we're going to do from there is we're going to discover the slope of the solution would be going through this orange point and do a new tangent line, and then use that new tangent line to predict where the next one is, etc. Right, so this is the general idea behind using Euler's method. To find the slope of a solution, you simply have to plug a point t comma y into the differential equation and find out what y prime is, and I'll tell you what the slope is. We'll do that here in a moment. But first, let's do a quick review on how to use a line to find a new point. So if we start at a point, I'm going to draw a little image down here. Let's say this point, we're going to call it t sub 0 comma y sub 0. And we happen to know the slope of a line passing through. So I'll just draw some sort of line. Okay, so then if I go to the right a certain amount, let's say we go to the right an amount that we're going to call h. The question will be, how far up or down do I need to go to get back to the line? So that we can find this second point right here, which we will refer to as t sub 1 comma y sub 1. And then we would repeat. Start with this as our starting point, do a new triangle with a new line, and call this one here t sub 2 y sub 2, etc. But let's just go over how to find the very next point. Well, if you recall, the slope of a line, if you know the slope of the line is the change in the dependent variable over the change in the independent variable. So delta y, which is this right here, is really just equal to m times delta t. But the h, we're using h for the delta t. So we'll say delta t is the same thing h, and delta y will be m times delta t, or in other words, m times h. Let's get rid of this. So we know that if I want to find y1 or t1 y1, t1 would be the same thing as starting at t naught and adding h to it, and then y1 would be starting at y0 and adding m times h to it. And then of course this generalizes. If you want to find t sub n, then you're going to do the previous, let's call this m by the way. Let's say this line here has slope m sub 0. It's the slope of the line that is going through this point here, t0, y0. So I'm going to call this m sub 0 in our notation, and down here as well. Because the m's don't stay constant when you go from point to point, because every time you get to a new point, you figure out a new slope of a new line, get to this point and figure out a new slope. So you always are working with a brand new slope every time you're going from point to point. So in general, t sub n will be equal to t sub n minus 1, the previous t, plus whatever h is. And we will let h be consistent though. We'll keep h constant step size. And y sub n can be found by doing the previous y sub n minus 1, and adding to it m sub n minus 1 times h. So this is our general formula for going from one point to the next. But each step along the way, you got to figure out the new slope and then calculate your new point. Okay, so let's go ahead and get this done for this first equation, for the specific example we have here. Let's go with orange. To find the slope of the solution through the point 0, 2. Remember, we did this when we did direction fields. You plug in t equals 0 and y equals 2 into the differential equation and solve for y prime. Well, notice our y prime is already isolated. It's y prime equals 0.5y. So we just have to plug in 0 and 2 into the right side of this differential equation. This side over here we're referring to as f of t comma y. It's some expression that involves t and y. Now, in this particular case, there is no t. So this is considered an autonomous differential equation. It's only dependent on y. But we still try to plug in every point t comma y and plug it into this right side of the differential equation. So the first point is right here in our table. We're considering our 0th point, our starting point, and the coordinates are 0 and 2. Remember, the input is the 0 and the output is here, the 2. So 0, 2 is our point. And we're going to plug that into this f function. This is what this is referring to. And this, of course, will give us the slope that we're after. So plug in 0 and 2 to 0.5y. The 0 has no place to go, but the 2 does. 0.5 times 2 is 1. And so we get 1 value. That's technically our m sub 0. That's our 0th slope. The slope going through our 0th point, going through this point. Okay, so back to our drawing. Keep in mind that our scales are not the same, right? There's 1 unit here horizontally, but 1 unit vertically. So when I draw a slope 1 line, it's not going to look like a slope 1 line. It won't look like a 45-degree angle because of the distortion. Start at 0, 2, go right 1, go up 1. So there's going to be our point right there that we want to connect to. And let me draw that line right now. Okay, that looks about right. And then, of course, we only want to use that line to find the very next point. So the little triangle I would draw here would be a triangle right here, go over 0.5 and up a certain amount. And so the point on the line that we're trying to find is this little orange point, just barely below the black point. So let me bring this line back and stop it right there. So there's our tangent line going through the point 0, 2. It has a slope of 1. Our h is 0.5. And then our delta y is the slope of this line. It's m times h, which in this case is 1 times 0.5. So it's also 0.5. And so our new point, we'll call it t1 comma y1. Forgot the 1. T sub 1 comma y sub 1. T sub 1 is found by doing t sub 0 and adding to it h, and y sub 1 will be found by doing y sub 0 and adding to it mh. And I should say m sub 0h. Let me keep forgetting to put the subscript on the m. So this is m sub 0 times h. M sub 0 times h. You can also say m naught. M naught is the naught. The word I'm saying naught is N-A-U-G-H-T. So I'm saying m naught. That means m nothing, m sub 0. And let's continue with our calculation. So t naught was 0 and h is 0.5. Y naught was 2 and m was 1 and h was 0.5. So we're just adding 0.5 to 2. So we get to the point 0.5 comma 2.5. Or we could say 1/2 and 5/2. But notice, compare this y coordinate to the exact solution y coordinate. It's close, but it's a little bit lower, as expected from the image. And we can fill in now our table over here. The t is already filled in for us, but the y we just determined was 2.5. Okay, now we want to make another triangle, starting at t1, y1. So to find the slope of the tangent line through t1, y1, we plug t1, y1 into our function f here. Again, the 0.5 has nowhere to go because there's no t's in this differential equation, but the 2.5 does. Plug in 2.5 for y, and 0.5 times 2.5 is 1.25. This will be our m sub 1. So we would draw a slightly steeper line than we drew before. I'm just going to approximate it. So something that looks a little bit steeper than it did before. We'll make a right triangle out of this. And our goal here is to find that point right there. Now again, the h is going to be 0.5. We're going to go to the right 0.5. And our delta y will be m sub 1 times h. Let's move that over. Okay, so our t2, y2 is that we're after next. The red point in our image. t2, y2. t2 will be found by doing t1 and adding h to it. And y2 will be found by taking y2 and adding to it mh. T1 was 0.5, and we're adding to that h, which is also 0.5. Y1 was 2.5, and we're adding to that m. M is 1.25, and h is 0.5. So that gives us a first coordinate of 1, and the second coordinate is going to be, let's see, a half of 1.25 is 0.625, and add that to 2.5, so we have 3.125 in the end is the y-coordinate from our calculation. Compare this y-coordinate to the actual y-coordinate. And you can see it's lower as expected, but not too far lower. So we got 3.125 here for that next y-coordinate. Then here we're going to say we don't need to find a slope at this point. We would if I wanted to keep going over here and do another triangle and find another point. But we're going to stop this process by hand right here. So let's just say in our table right here that there's no need to continue. We'll stop here. Okay, now you are probably wondering, what can we do to make the approximations even closer? And the one answer to that is simply do a smaller h value. We call that the step. Do a smaller step value. And what if h was 0.1? Then we would have a whole bunch of little triangles to draw in order to traverse this same distance here. Can you imagine 10 little triangles in there instead of 2, right? If h was 0.1 instead of 0.5. But each triangle, I mean, the closer, in general, right, the closer you stay to where a tangent line is tangent to a curve, like if you have a curve and you have a tangent line, right, if you stay relatively close to the tangent line, then your tangent line is a better approximation, right? The further you go away, the more potential you have for divergence from the tangent line. So smaller step values will be one way that we do this, but we're not going to do it by hand. We'll be doing this with technology. And what I'd like to do next is show you the technology to repeat what we just did on this one slide. So first thing you want to do is log into Canvas, and on the home page in the schedule, there I put a link next to homework 10. It says homework 10, Euler's approximation, and then there is a link said spreadsheet. Click on spreadsheet, and it's going to open this Google Spreadsheet. Now, it'll be view only, so you can't edit anything. And don't click on request edit access. Do not do that, because I won't share access with this. This is my file, and if you edit it, it'll edit it on my end too. So if you want your own version of this, instead go on File and select Make a Copy. This will put a copy into your Google account, and you can see your Google account. Make sure you're logged into the right account over here that you want this to make a copy to. And then you go to File and Make a Copy. And once you have your own copy, you'll be able to edit this. Okay, now there is some work and some training using the spreadsheet that we need to do together. The only fields that you need to change are the white ones. So the initial condition, what's your t naught, y naught, plug that in here, and then your step size, whatever h is. And then you have to plug in a formula that does the correct f of ty, given the input data. And that's going to be the hardest part of this, but with a little training, you can get good at it. And then you want to copy that formula down for all of these. And I'll show you how I built a macro into this so that you can do that quickly instead of clicking and dragging, because if you scroll down, I designed this table to go quite far down. It goes down all the way to 1,000 in case we need to have lots of data. Okay, so let's look at the example we have here. T naught is 0 and y naught is 2. So that's correct in place. Our h was 0.5 in the example we did, so I'm going to change this to 0.5. Notice that all the t's automatically line up, and then the calculations here are automatic too, but they are dependent on what you enter here in this field. Let me delete this, whatever formula is there. Every time you go to a new function, you want to delete this formula and enter a new one. Now this formula, y prime is equal to 2 times y. So what we want to do is we want to enter in this cell 2 times the value that's in the y cell. So I'm going to you put an equal sign, then you do a 2, then the times sign, and then you simply click the cell where the y coordinate is. And it says cell G3. And then you hit enter, and this, you'll notice that whatever you see right here is always just double the y coordinate. I don't know why I said double. Our function is not 2 times y, it's 0.5 times y. 0.5 times the G3. There we go. There's the slope that we were expecting, the slope of 1 that we got in our table. Now, the problem is when you enter the correct formula here, the next one down is the previous one. So all of these down are all the previous. So you could scroll all the way down and delete all this stuff. This is one way to do it. Just delete everything, and then click on here, hover over the very corner till you see the plus sign, and then drag down. And what that does is whatever formula you put here, it drags down a comparable formula, a formula that is relative formula. In other words, if you click on one of these and click up here, notice what it's doing. It's doing 0.5 times this cell, which is exactly what you want it to do. You always want it to do 0.5 times the cell immediately to the left. So that's one way to get the correct formula in there. Another one is enter the correct formula here and then follow these instructions. Enter the appropriate formula in cell H3, then run the macro copy formula under tools. So if you come up here under tools and go to macros, there should be a macro that says copy formula. And here's a shortcut for doing it. Click on copy formula, and it's going to fill this entire column all the way down to the 1000th entry with that formula. So that way you don't have to scroll all the way down every time when you want to copy the formula down. So you have to do those 5 things, right? 1, 2, 3, 4, and then follow these instructions 5, and then everything will be correct for our particular differential equation. Now we only went this far in the table, right? Those entries right there. You can compare them to what we did by hand. Over here, there's a plot that just does the first 10 data points. You could change the settings on this image, or you can go to Desmos and plot these points too. This is the way I'm going to actually recommend you do it. This image here is just to see if things look right in case you want to, if your formula is wrong somewhere, then a point might dramatically be far away. So this is just a quick glance to make sure you copy the formula right. You should see some sort of smooth progression of points. But I don't really use this table much. Instead, you can go to Desmos, open up a Desmos. And Desmos is really good at just copying tables of data. For example, if I wanted to copy just these first set of points, just do Control Copy. Go to Desmos, go into your input field and paste. And it makes a table for you with that data. And what's nice about this is we can graph the exact solution here too, which was 2e raised to the 0.5 t. Or you can put x there too, it doesn't matter. It recognizes t or x as independent variables. And we can do some dragging here to make this kind of look like what we had in the other image. And sure enough, you see our approximating points. They appear to be getting worse, right? Because we're starting with, if I were to find the next point, I would expect the next one to be even further away from the curve because the error keeps compounding. Also in Desmos, if you want to make a line graph out of those green points, hold over here and click on this lines, turn on lines. And notice it makes a little line graph connecting your points with straight line segments. Okay, let's return to our notes and do the next one. Now, this process is greatly sped up by using technology. Duh. Use technology to perform Euler's method to approximate the solution to the ODE for the time interval 0, 1 using the indicated step size. Compare the approximation to the exact solution. Okay, you'll notice that we have the exact same differential equation here, the same exact solution. Step size is specified to be 0.2, so you'll notice your t's go up by 0.2, and we're going to do the table until we cover the entire interval from 0 to 1. So as soon as I get to t equals 1 is where I stop. And all we have left now to do is fill in these points here. Notice I don't have the extra column over here to find the slopes because we're not doing this by hand. I just want to fill in these y coordinates. And then the graph you're seeing over here is the exact solution. Okay, so returning to our spreadsheet, we have already the correct 0 and the correct, the correct t naught and y naught, 0, 2. Step size, we want to shrink to 0.2. Hit enter. And then, of course, click on this cell and make sure we're doing the right f function, which is 0.5 times the y coordinate. So that looks good. And that's already the same formula that's in all these cells, right? You pause anytime, you'll see it's 0.5 times the y coordinate next to it. So we don't need to do these last few steps because we're working with the same differential equation. So now all I have to do is copy the amount of table that's from 0 to 1. I'm going to copy that. Come over here to Desmos. Let's just get rid of this table and put a new space and then paste. And let's go ahead and turn on those lines. Let me go ahead and put in the former 0.5 step size and copy this amount of data from 0 to 1, which is fewer points, and paste that as a new table over here and make it a different color. Let's make it stand out orange and turn on the lines. And we can hide the original function too so we can see the two. Okay, so what's happening here? Our orange table, when the step size is 0.5, only generated a total of 2 extra points, so 3 points total. The green one did step size of 0.2, so it generated even more data points along the way. And if we zoom into one of these, we'll see that that point appears to be on the orange line because we were using the same slope to find that first green point as we found for the first orange point, right? We used the slope at 0, 2, which was 1. So we expect the first green and the first orange to be on the same line segment. But after that, once we got to the first green, we plugged it into the function, got a new slope, and got a slightly steeper slope. That's why it's taking us to a slightly different location. It's a little bit higher than where the orange line is. And by the time we got to the end, our green dot approximation was higher than the orange. Now let's go ahead and put the exact solution in here. And let's put a vertical line at x equals 1 so we can compare the exact and then the two different approximations. Now, they're not highlighting for me, unfortunately, but you can see them over here in the table. Okay, so the exact value on the solution when t is 1 is 3.297, the black point. Our green method approximating gave us 3.22, and the orange got us to 3.125. So the green, of course, did better. It outperformed the orange. That's simply because we did a smaller step size. Now, there were more calculations to do in order to get that improved accuracy. Back to here, and we should fill in. Let me put the step size back to 0.2, hit enter, and then I'm just going to take a moment and fill in some of the data here from our table. Make sure you do this in your solutions too, or on your guided notes. Don't just turn in a blank page here. So when t was 0.2, then the y coordinate was 2.2. Now I'm just going to copy from the table. Then we had 2.42 was the next one, then 2.662. And when t was 0.8, we had 2.9282. And at some point, we want to stop, round to a certain amount and then say this is good enough. Your homework will specify to what decimal position you should round all your numbers. And finally, when we got to the 1, we had 3.22102. And for color coordination, let me change these colors. I'll make them green. And let's plot some points here in our solution. So when t was 0.2, we had 2.2 was just barely below the exact solution. When t was 0.4, we got 2.42, just barely below, but slightly further away from the exact. 0.6 gave us 2.66. So the gap between my approximation and the real one should increase as we go from point to point. 0.8 was 2.92 something, was somewhere in there. And then finally we had 3.22. So it was somewhere in here, plotting those points. And let's not bother writing anything else on this page. Most of the work was done by the technology for us. Let's go to the next one. Repeat the last task, but use the new indicated step size. Compare the approximation to the exact solution. Okay, the only thing that's different now, everything's the same here, but we're doing a h of 0.1. So I'm going to return to my spreadsheet and change h to 0.1. Nothing else needs to change. Let's go ahead and fill in our entries here. So we had 2.1 is the first one. Then we had I'm going to round to the nearest tenth. So 2.205 goes to 2.21. Sorry, nearest hundredth, I meant to say. So 2.32 is the next one to the nearest hundredth. 2.43 comes next. 2.55. 2.68. 2.81. 2.95. And 3.10. And then finally, when we get to t equals 1, we have a 3.26 rounded. 3.26. And what's going to happen here is we're going to get green points that are even closer to the black points. When you actually plot these points, the gap will get further and further, but overall it'll still be a better approximation than we had when we had h was 0.2. And to confirm that, let's go ahead and copy all the data up until we get to t equals 1. I'm going to copy that, go to Desmos, and let's create a new one, a new table, paste it. Let's make its color be something else. Let's go with red. And let's put the lines. Okay, now specifically, if I were to zoom in anywhere, any one of these locations, you would see, let's go to, yeah, like you'll see that the red is an improvement even on the green. And if you go to the very end, there we go. For some reason now I can click on them all. So there's everything. The exact y coordinate when t is 1 for the exact solution is 3.297. And you can see the red is the closest. It's the best approximation, then the green, and then the orange. Okay, back to our notes. We just have one more to do. This time we're switching the function, though. So our differential equation is y prime equals, oh, and we're going to do an interval from 1 to 3, so just trying to change some things up. Step size will go back to 0.2. Our differential equation is y prime equals negative 2ty squared, and y sub 1 is 1.25. Now the exact solution, this is also separable, and so it's easy to solve, and here's the exact solution, 1 over t squared minus 0.2. And a graph of the exact solution is over here with points on that curve. And just to make sure we understand how I would find the first slope, right? When you plug in your initial point, which is 1, 1.25, so there's my t sub 0 and y sub 0. You plug the t and y into your differential equation right here, and you would calculate a slope. And then you use that slope, right, to make a prediction on what the next point's going to be. Okay, so returning to the software, open up the spreadsheet. We have several things to change. Everything has to change. The initial t is 1. The initial y is 1.25. The h will be 0.2 in this case. And we got to change the function. The differential equation is new. So click on this H3 cell, delete this, and say equal. And now we're going to follow the instructions of the differential equation, which is to do negative 2 times t. So negative 2, you have to write the times sign when you're in these spreadsheets, times the t coordinate. The t coordinate is f3. So just click on that. It'll put the f3 there. But then we have to multiply this by y squared. So do a times symbol, and then click on the y cell. There's y. And then you could do a caret on that g3 and say squared. So this is negative 2 times the t coordinate times the square of the y coordinate. And that's how we find the slope. And when you do that, you get this negative 3.1250. Now look at the dots. They don't seem to follow a pattern. At least these ones do, but from here to here and then dramatically different. That's an indication that we haven't yet copied our formula down. So the fast way to do that, of course, is to go to your tools, go to macro, and say copy formula. There. Now it's copied that formula down. You can verify, right? Click on any cell, click up here, and you'll see that it's doing negative 2 times the t coordinate, which is 2.8, times the square of the y coordinate, times the square of that cell. So just confirming that we're doing the right calculation for each of these. And you can see now the pattern that we expected to see. All right, so in our notes, let's fill this in. Let's take the moment to do this. You can fast forward if you don't want to watch me do this, but the first y coordinate was 1.25. The next y coordinate, and I'm going to round to the nearest hundredth again, so about 0.63. Just reading off the table. Next one's about 0.44. Then we had 0.33. Make sure you're looking at the y column, right, not the f column. Then we have 0.26. By the time we get to a t coordinate of 2, we're at 0.21 for the y coordinate. Then we're at 0.18, followed by 0.15, then 0.13, just rounding to the nearest hundredth again. 2.8 gave us 0.11, and then finally the 3 gave us 0.096 rounded up, so 0.10 is the rounded version, 0.10. If you're to plot all these points, this graph is concave, so when you do a tangent line and you put a point on a tangent line, you can see it's going to be below the exact answer. So we can expect all of these. I haven't graphed them at the same time yet, but I'm anticipating that all of these will be lower than the exact answer, and the gap will get worse and worse as we keep going. Maybe it'll start to improve too. Depends on, actually we can expect an improvement perhaps on the approximation. Think about that. Because the graph is flattening, do we expect the approximation to improve and get closer again? That's something worth thinking about. Okay, let's plot this data now from 1 to 3. So I'm copying in the table from everything from 1 to 3 for the t's. Copy, go to Desmos. Let's delete all this stuff. We don't need any of this anymore. And paste that new table in here. Let's make this have the lines. You don't have to do that, but now let's type in the exact answer, which was given to us. It's y equals 1 over t squared minus 0.2. We do have this sort of convergence. Notice the vertical gap between the exact solution and the approximations does appear to be improving because of the flattening of the graph. So something to think about. Try to understand why that's the case here, why that's improving upon itself. So I'm going to do some revision and try to draw something that's more accurate about what really happened here. So 0.63 was here's about there somewhere. I don't know why that didn't draw a point. There we go. Now I'm trying to just look at these numbers here and place these points more accurately. 0.44 is somewhere in there. Now keep in mind each of these is 0.1 going up. 0.33 is in this area. 0.33. 0.26 is right around there. 0.21 is just above 0.2. 0.18 is right around there. 0.15 right in there. 0.13, we do seem to be getting closer, right? To 0.11 is just above, and at 3 we're at 0.10, which is barely below that point there. So we actually see sort of this improvement of the approximation over time. And when you think about it, that's going to have to be the case, because both of the approximations and the solution itself will approach the x-axis, so they will be pinched together. The black curve will sort of pinch the approximations towards the x-axis. So as time goes on, our solutions actually get more and more exact. Our approximations, I mean to say, get more and more exact. Okay, and that is everything for this lecture on Euler's method to approximate solutions to ODEs, first order.